All right, we're officially recording. So if you're coming to the recording because you unfortunately were unable to show up to the review, welcome. This is going to be the review for COT3100, that is applications of discrete data structures for exam 2. We're reviewing hopefully all of the content that will be on the exam. As I usually do, I want to go over my normal disclaimers. No, I'm not a professor. No, I'm not a TA. Therefore, there could be things that are wrong. Like in the slides or anything, if you notice something that's wrong, make sure to point it out. The goal here is not to spread misinformation. It's to, make sure everybody actually reviews and learns. So once again, if you notice something wrong, just feel free to point it out and let me know. And that way I can get it changed. And so when I release the slides later, they're all correct. With that being said, my goal here is just to be going over a review of all the content that we learned for exam 2, starting with sets. And I guess if I go a slide forward, we can see right here. Here's basically for our exam 2 topics. Here's our basic, what we're going to go over. So we're going to go over set logic, very similar to propositional logic, but with different symbols. A lot of people compare discrete to learning a new language. And I think that's pretty much true. There are hints of statistics and probability. If you took a stats class, whether it be in high school or college, whatever, you'll probably notice that you already know some of this stuff. Then we're going to go over functions. We're going to go over their descriptions. We're going to go over summations, which really goes into Calc 2. If you've already taken Calc 2, then you'll know that summations are very extensively covered in that class. And then finally, we'll go over algorithms. And algorithms include searching, sorting, and time complexity, all of that sort of stuff, big O, big theta, big omega, stuff like that. Okay. So hopefully we can get through all of this, and I have some examples that I'll go over with you guys so that hopefully you can begin to gather a lot of the logic that you'll be needing to use on tomorrow's exam. So we have set logic part 1, basic symbols. We do need to know basic vocabulary for this exam. It's going to be important. So let's go over what all these symbols mean, right? So here you go, red. What's this, guys? Denoting a set, okay, that sounds good to me. Denotes a set. And what's this one right here? Union, and what is this equal to? Or, yeah. And notice that, remember from last unit for last exam, what does this kind of look like? Does it kind of look like this? Yeah, it does. Okay, and now what's this one right here? An intersection, that's what I'm hearing, which is correct. So this is an intersection, and what does this denote, guys? An and, cool. And what does this look like? Yeah. All right, so now we get to some new symbols, some wacky symbols that we see here, and I'm going to explain these. So first of all, we have this. What does this kind of look like in a different mathematical sense? What does this kind of look like? This kind of looks like a less than or equal to sign. You see that? So what this really means is we're saying that this is a subset. Something is a subset of another thing. So if we had like A, B, this would mean is a subset, okay? Now for this next one though, now notice how all of a sudden we no longer have this little line down here. We don't have a line. So without that line, that means that we're no longer including the case where the subsets are equal. And this is what's called a proper subset. In this case, we need to keep in mind that for a proper subset, if the two sets are the same set. So let's say we had one set that was 1, 2, 3, and we had another set that was 1, 2, 3. Let's just say set A and set B. We could say that set A is a subset of set B, but we could not say that set A is a proper subset of set B because it's not less than, it's the same set, if that makes sense. So hopefully you can kind of understand the difference between these two right here. It is a minor difference, but it is an important one because it might show up on the exam. Now then we have, this is called a superset. It's basically the opposite. It's saying that one set has greater than or equal to the amount of members in another set. And then here we have the proper superset, which with the same logic as the proper subset, this is saying that a set has more members than another set. It's not has more or equal to another set. It just straight up has more. So if you have equal, then you are not a proper superset of another set. Right. So like, yeah. Okay. So then after that, do you guys have any guesses of what this is? It's kind of like you can kind of figure it out based on looking at it. It just means not a subset. Right. This is not really super necessary to know, but oh no, what did I almost wrote subject? let's see, not a subset. So then we have this up here. What is this? This is kind of, this one up at the top right. Maybe people can guess. What is this? Yeah. So in terms, we would say that this means a difference. So if we had A minus B, right? What would that mean? Right. So all the elements in A, but not in B. Okay. And what does this mean? This is part of the set. And what's this next one? Is not part of the set. Obviously, whenever I release these PowerPoints, you'll get the annotated versions, so you have all of these definitions. Now, what is this? This is the null set or the empty set. And what does this actually mean? This means that basically a set is empty, which there's nothing in a set, right? So if I said a set was this, oh gosh, that was so bad. If I said this was your set, basically your power set of this would just be this. However, we will get into power sets later and go over that stuff, so don't worry. Now this, you might be thinking, why is there just a big U there? Isn't this the same thing as union? No, this is actually a different thing. This is for your universe of discourse. This is the symbol that you use for basically all of the elements in something, in a set. What's up? Note that null is not equivalent to null. Yes, so this, somebody was saying in chat, this is not the same thing as this. Which what this is saying is this is the set that includes null. And this is just the empty set. See that? Okay. So yeah, anyways, this means your universe of discourse, which is everything that that is included in a set, your domain, range, codomain, whatever you want to call it, everything that you could include. And then what is this? Any guesses? Power set, and in this case, it's the power set of A. And we will be going over that. Now, what is this right here when we have this little X sign and assuming that A and B are both sets? A Cartesian product, yep. And we will also be going over how to perform those. And then finally, what does this mean? Now, this is if you're taking like calculus or physics or whatever, what does these absolute value bars usually denote? Magnitude. So if you think about magnitude, what is magnitude? It's a number, right? So if it's a number, then what would this mean if we were taking the number in a set? It would be well, it is called the cardinality. I heard it in the audience. And it's basically the number of elements in a set. All right, so now we get to move on and we get to start going from just definitions to actually doing stuff with these definitions. Here's the answer key in case you needed it. So now we have all these laws. You'll notice these laws, we've seen them in the past, and this is where I believe we'll probably have some form of proofs to do. Notice that these laws, they're basically all the laws from Unit 1. However, they're now put into set logic instead of propositional logic. We have different symbols. For example, I think if you remember, like if we look at this law right here, in propositional logic, it was something along the lines of A and true is equal to A. But now we have basically A and the universe of discourse is equal to A, or this would be similar to A or false is also equal to A, etc. We could theoretically go down each one of these laws and we could pair them up with the same exact propositional laws that we learned last unit. So if you want to review these, I'd say review them, put them next to the propositional laws, think about them, and hopefully you can get them. Obviously, make sure you know De Morgan's law. It's down here. That is a negation. When you take the negation of something in parentheses, remember that if we're going from like a union, we're going to go to an intersection, and if we're going from an intersection, we're going to go to a union. So if things flip, I'm just going to write that here. And I highly recommend that you have all of these laws written down on your little handwritten formula sheet before you take the exam, just so that in the case that you do forget one of these laws, or in the case that there's a proof, you can have them all right there, and you just simply copy them down. All right, so now we get to do actual problems. So we have power sets that I wanted to go over first. Now, remember that I have this written right here. Power sets always have 2 to the n cardinality, right? Now, remember that if we have just the empty set or the null set, and it's not an actual set itself, that means we have a set with 0 members. Now, what is 2 to the 0? 2 to the 0 is 1. Keep that in mind. So now we're going to take these power sets, and while taking these, we're also going to note the cardinality of each set. That way we can get some good practice. So we have the empty set here. I just said it. How many members do we have? What's the cardinality? Cardinality, no. This is the empty set. Cardinality 0. So we're going to have 2 to the 0 total numbers in the power set of this. So which is equal to 1. Now, if we have one number, I mean, it's kind of obvious of what it's got to be, right? There you go. That's it. So now we move on. We have the set with the empty set, right? Now, the set with the empty set, how many numbers do we have in this set? 1. So if we have 2 to the 1, that's equal to 2. So we're going to have 2 numbers in this set. Now, what do you guys think is the first thing? Yeah, the null set. And what's the second thing? Well, it's the number in the set, right? Which is the set that includes the null set. There you go. So that's our answer for that one. Now we have a little bit something that's a little bit more intense. But how many total numbers do we have in this? How many? Hold up. I have 4, but think about this for a second. We got 1, 2, right? So it's just 2. But then so that, yeah, okay, I see what you guys are saying. 4 total members in the power set, right? Is what you're saying. Okay. So 4. So now, so we're going to start with our null set, right? And then we're going to put, basically you're going to want to put your 2, anything, after you list the null set, just go and list the individual members of the set. So we're going to list this, which is this guy right here. And then we're going to list this guy right here. But notice how this guy originally already has some of these. So now we're going to have to put 2 of these, okay? 2 brackets. And then finally, we've listed all of our individual members. So now we're going to have to list all the combinations of the members combined. So we're going to, in this case, there's only 1. It's just you have both of them. And I think that's it. Notice we have 1, 2, 3, 4. See, do you guys see that? Does that make sense? Hopefully. Okay, cool. So now how many members do we have in this set? Yep. So 2 to the 1, and we're going to have a total of 2 in the power set. Notice that this is really the same thing as this, just we have an A instead of an empty set right there. So we're going to say the power set is going to be, yeah, the null, and we have A. Gosh, my handwriting is like, these brackets are killing me, but it's okay. So how many do we have here? We have 2 to the power of 2, which is going to be 4. So then right here, what we have is we're going to have the null set. We're going to have A, B, we're writing out our individuals, and then we're going to have A and B. And finally, we have one with 3. So this one's going to be a little bit more content. We're going to have 2 to the power of 3, which is equal to 8 total. So if we write this out, we're going to have our null set, and we're going to have all of our individual members. Let's see. So we're going to go A, and then we're going to have AB, which is another individual member. And then after that, we're going to have all the combinations of our individual members. So for example, we're going to have the null set and the A. And actually, let's see. Hold up. Yeah, that works. And then we're going to have the null set and the AB. And then we're going to have the A and the AB. And then finally, we're going to have all 3 of them. And if we count this up, we should get 1, 2, 3, 4, 5, 6, 7, 8 total numbers. Do you guys see that? Hopefully that makes sense. And hopefully it's a decent enough review so that when I can guarantee you we'll have some problems like this on the exam for these power sets. All right, so now we have the answer key for that. That's cool. Then we have Cartesian products. Cartesian, not sure how to pronounce that, but that's kind of irrelevant. We're going to start off with saying, how do we find how many total members that we have? Also, let me do something real quick. There's supposed to be I'll fix this like this for now, but I'll have to fix it later. There's supposed to be a little multiplication symbol there. But anyways, we can tell how many items we're going to have in a Cartesian set by basically taking the total numbers of the first set and the total numbers of the second set and multiplying them together. So for example, for this one, we're going to have 2 total times 1 is equal to 2, right? So then if we actually write the Cartesian product, basically what we're going to do is make all the different combinations of these sets. So for example, we could have a 0 and a 2. We might put it like this. Actually, I think when they write it in the textbook, they put it like this. Put 0, 2, and then 1, 2. So do you guys see how that's performed? You just like take it and you do both different combinations. Any questions on that topic? No? Okay, cool. So then we're going to take this and we're going to do the same thing. We're going to go 0, 2, and notice this has a 2 times 2, so it should be probably 4 total, right? So we're going to go 0, 2, 0, 3, 1, 2, 1, 3. Now we have 3 by 3. Now, with this 3 by 3, we're going to have a total of 9, so it's going to take a fat moment to write. And notice that for these 2 sets, right, for this one and this one, they're actually going to be the same, just one of them is going to have numbers and one of them is going to have letters. So I'm only going to do one. If you guys have no questions, then I'm not going to do the second one because literally they're the same thing, just using letters instead of numbers. So this is going to be right here. We're going to have, and also notice because there's still only 2 total products though being multiplied, so we're still only going to have 2 members in each like set type thing. So we're going to have 0, 3, 0, 4, and 0, 5, and then we're going to have 1, 3, 1, 4, 1, 5, and then we're going to have 2, 3, 2, 4, 2, 5. So for this one, for this one right here. Yeah, you multiply 1 half and multiply whatever you have. So I'll show you how I do these, or my process, obviously. I'm not sure. Yeah, you can probably just take this and multiply them out. And you're saying like do them separately type thing. So yeah, so notice how in this one and in this one, right? And I'll probably just do this first one because obviously this one is just a longer version of that one. But notice how now all of a sudden we have 3 total products being multiplied, right? Or not products, like whatever you want to call them. We have 3 sets being multiplied, which means that each individual set of parentheses is going to have 3 objects in it, not just 2. So what we're going to do here, I'm going to start, basically we're going to have 0, 2, 4, and we're going to have 0, 2, 5. And then we're going to have 0, 3, 4. And we're going to have 0, 3, 5. And then we're done with 0, right? So then we're going to have to go on to 1. We're going to have 1, 2, 4, and 1, 2, 5. And then finally, we're going to have 1, 3, 4, and 1, 3, 5. Now, if I do this, right, this is 2 times 2 times 2, which is 8. So we should have 1, 2, 3, 4, 5, 6, 7, 8. So good job. Okay, so do you guys see how to do this process? And do you see also how to check yourself with just multiplying to see the total number of values you have? I think that's a good check. If you're just on an exam and you did it quickly and you just want to make sure like, oh, I didn't like accidentally like miss one or add another one or something along those lines, you just multiply it and make sure your total matches. Yeah. Because so we have 2 times 2 times 2, which means that it's supposed to be 8 total, like what combinations, I guess you could say, call it, right? So there's the answer key for that. As you can see, this one would have taken a little while. So that's why I decided to skip that one. It would have been the same process. It was just longer. All right, now we have types of functions. We're moving on past sets. So first of all, we have a one-to-one function. Right, so what one-to-one means is that basically every output has only one input that matches with it. What I mean by this, let's say we had a function like x squared, right? Would this be one-to-one at all? Because no, because think about it, right? If we had x equals -2 and x equals 2, they're going to give us the same y. So that would not be a one-to-one function, and we'll get into that a little bit later more. But do you guys understand this definition? Every output has only one input that goes with it? Okay, cool. I was just making sure everything is like kind of making sense. But then on to what we could say here in fancy terms would be every member in the codomain is in the range or included in the range. What this means is that the codomain and the range are the same. What this means is that every possible value in the codomain or in the universe of discourse, whatever you want to call it, every possible value in the output is also like actually a factor that you can get, is a solution you can get by plugging in the input. So every output factor is actually possible to create using whatever function you're given. And then we have one-to-one correspondence, and this is basically saying both 1 to 1 and onto. All right, so now we get to go. We have the definitions down. Are there any questions on these definitions? What's up? Right, yeah, every input has only one value. Yep. Onto doesn't particularly mean there's one input on it. It just means that every output has at least one input. Yeah, but I'll go on. Hold on, Miley, but I'll finish.
One-to-one is every input has one value. Onto is every output.
Yeah, every output has the ability to like, yeah, has a value, yes.
But so one-to-one, like the range, we can't have, or wait, we definitely could have like an output that doesn't have an input fraction.
One-to-one, you could have an output that does not have an input, yes. Yeah. And we'll see that possibly right here. So now I have an example. Dude, I'm so proud of this slide. It was like so fun to make this one. They aren't supposed to. That's the fun of the game. All right, so let's figure out what these are. Let's look at this first one. What's it looking like to you guys? Onto, good, good, good. And is this one-to-one? No. And why is this one-to-one or not one-to-one? This is not one-to-one because of these two guys right here pointing to the same data set, okay? Now, what about this one right here? What is this looking like? The right one. Yeah, this one.
One-to-one.
Yes, that is one-to-one. And is this onto? So notice it is 1 to 1, but it's not onto. And why is this not onto? Because of this guy right here, right? This guy has no value pointing to him. And finally, we have this one, and this one might be kind of obvious. Which one is this? Yep, one-to-one correspondence, one-to-one correspondence. And notice that this is also called bijective. Just so you guys know, and remember that for bijective function, it just basically means that once again you have both onto and one-to-one, surjective and injective, which I get which one is like off the top of my head, but know those definitions. Write them down on your formula sheet for sure. Onto is injective, yeah, and then the other is surjective, correct? Yeah. So then if we move on though, once again, I would just Google those definitions and make sure you have them on your formula sheet. That way you don't mess them up on the exam. So then we have functions part 2. We're going to decide now, instead of just looking at these fancy graphs, we're going to look at actual functions like mathematical functions and decide what they actually are. So the first is the function f of x, where the universe of discourse for x is z. What's z? Integers, right? So x is the set of integers. The universe of discourse for x is the set of integers, and for y, it's also the set of integers. What is this looking like to you guys? We have just f of x equals x, or y equals x. If you bijective, yep, or one-to-one correspondence. Yes. So now we have f of x equals x, where x is part of the set of integers, and y is part of the set of real numbers. What is this looking like to you guys? One-to-one, but not onto. Yes. So the reason that this is for you in the Zoom, and for you who like, I don't know, want to know why, the reason that this is one-to-one and not onto is because we could plug in any value we wanted from x, right? And we would get a distinct value. You know, if we plug in 1, we're going to get 1. If we plug in 2, we're going to get 2. If we plug in -5, we're going to get -5, right? They all have their own distinct value. However, let's say the y is the set of real numbers, right? What is the set of real numbers? That includes -1.5. That includes irrational numbers that I couldn't even like, that includes like pi and stuff too, right? There was no possible way for me to plug in an integer and get, once again, for example, get like 1.5. That's not going to work. Thus, not all of the components in the domain or the codomain are actually, are actually possible to get in this function. That's why it is not onto. So then we have f of x equals x squared, where the universe of discourse for x is the integers, and for y is all perfect squares. What do you guys think about this one? Yes, I heard the answer in the audience. Correct answer is onto, but it's not one-to-one. Now, if you think about this, it's onto because once again, we said that we said the universe of discourse is all the perfect squares. And if we have all of if we have all the integers for x, then that means we can get all of the perfect squares. However, this is not one-to-one because let's say we had, once again, -2 and 2, they're going to give us the same value. So this is why that cannot be one-to-one. And finally, we have x squared, where the universe of discourse for both x and y is just all the integers. Any guesses as to this one, as what this one is? Neither? Yes. Because think about it. This would be neither. This one would be neither because, first of all, like I said, we can get like -2 and 2 would be the same. But on top of that, let's say we wanted to get an integer, which is part of y. Like let's say we wanted to get like 3. That's not a perfect square. It's not possible to plug in a value and get 3 when our function is x squared. Hence why it's also not onto. So hopefully, I know that these are very simple like examples. I'm hoping that they don't go super duper complex on the exam, but hopefully these at least help you brush up on the basic concepts of one-to-one. They get too complex, I'm being blamed. Can we go over the second one real quick? Yeah, sure. So the second one, we're looking at f of x equals x, where the universe of discourse for x is the set of integers, and for y, it's all real numbers. Now, notice that whatever integer we plug in for x, we're going to get a unique value. We're not going to get a value that's a repeat or anything. However, it is impossible to make all real numbers because we're just plugging in integers and then saying that the function's value is that integer. So it is impossible for us to get something that is like 1.5 or 2.5 or any fraction or any irrational number. We can't get that. And that is part of Y's codomain. So because we cannot fill the codomain, our range is not the entire codomain, so therefore it's not onto. All right, no problem. All right, so now we have manipulating functions. We also have to do this. I don't know if you guys remember doing this all the way back, like what, like algebra 1, algebra 2 or something, right? Yeah, but I didn't really actually prepare an actual example for this. I was planning for you guys to just give me some functions. What functions do we want to use?
3x to 4.
3x. Okay, so f of x is equal to 3x. I'm going to do something like slightly more complicated, okay? I'm going to say g of x is equal to x plus 1, okay? There's a reason for this. So what would f of x be or what would f plus g of x be? 3x plus x plus 1 equals 4x plus 1. I'll go over this very quick because I know that like a lot of you do not want to come here and learn algebra. So we have 3x, and then we have minus x plus 1, which is equal to 2x minus 1. And we have f times x, so we're going to have 3x times x plus 1, which is going to be 3x squared plus 3x, right? Then we have f over g of x, which in this case, it's just going to be 3x over x plus 1. I guess if you wanted to get technical, right, you could say x is not -1 or something, because that would make it undefined. Then we have f, and we have this little open circle g. What does that mean? Do you guys remember? It's a composition, and what do we do for a composition? We're going to plug g of x into f of x. So we're going to say f of x is 3x, right? Basically, what we're going to do, we're going to take away this x, and we're going to replace it with the function that is g of x. So it's going to be x plus 1, which is equal to 3x plus 3. And finally, we have the inverse of x. Now, notice that also this is just for f. This is not for, g. But for an inverse function, basically what you're going to want to do, once again, if you remember from algebra, you basically swap the x and the y, and then you solve for the y. Now, also keep in mind with an inverse function, it needs to be bijective. It cannot be, if it's not a one-to-one correspondence, you cannot do an inverse of a function. So if you get like a question that says, does this have an inverse? Usually you can just check, like, is it one-to-one? And you can usually figure out whether or not it has an inverse or not. So keep that in mind. So let's see, this is going to be really simple. Let's see, we have f of x is equal to 3x, right? So what we're going to do here is we're going to replace, first we're going to say this is the same thing as y equals 3x, right? So I guess I could actually erase this and say, instead of an arrow, I could say equal, right? But now what we're going to do here, the next step, however, we're going to flip them, and we're going to get basically x equals 3y. And then we're going to go this way, and we're going to say that this means that y is equal to x over 3, right? And then finally, we can replace y with f of x if you really want to, or you could say, well, this is going to be the inverse, which is equal to x over 3. Now, I noticed that in the homework, sometimes it forced you to solve for like f -1 of y. Keep that in mind, that that's just the same thing as replacing x with that. So yeah, but in this case, I just solved for f -1 of x. Does everyone understand these? Once again, they're more algebra concepts. I didn't want to spend too much time just because like a lot of people are like, why are you spending time on stuff I learned in middle school? But it would have a plus or minus. So it wouldn't, yeah, I think they're talking about, let's see, somebody answering somebody else's question. Yeah. Okay, cool. Yeah, they're currently talking about just domains and stuff from earlier. I don't think they're actually asking any questions that could be wrong. But anyways, we're going to continue on. We're cruising through this. You guys have like no questions today. Wait to algorithms? Okay. Oh my. We are cruising. You're sitting here like, man, we're going fast. This is crazy. But all right, so we have an arithmetic sequence. So what would an example of an arithmetic sequence be? Just be like 1, what am I doing? 1, 2, 3, 4, or we could have like 2, 4, 6, 8, right? We're just adding a number over and over again. And we have a geometric sequence. What is this like? Okay, let's say we had, we started at 1, and we went to 2, 4, 8, 16, etc. And then we have this thing called a recurrence relation, which is basically, it's not the general form. It's not just putting it into a, like it's not getting you a direct formula based on n. What the recurrence relation is doing, notice it kind of sounds like recursive, it kind of sounds like recursion. So you're basically going to be doing something based on the last object in a value. So for example, if we had like this series right here, right? We could say that the recurrence relation for this would be a of n is equal to a of n minus 1. And it's just the value before it plus 1, right? That makes sense. Or if we had like this right here. Now we would also want to define for this. We would want to define a of 0 or a of 1. Basically, the first member is going to be 1. Or whatever you wanted to define that for that. But anyways, then for this right here, right? We could once again say the first member is going to be 1. And then we're going to say that a of n is going to be, now we're just multiplying by 2 for this geometric sequence, right? So it's just going to be 2 times a of n minus 1. Okay, does that make sense to you guys? Okay, cool. Picture, okay. Well, I got the shot. Okay, cool. All right, so right. So if you were solving for one using these formulas, right? Because they're not the general, it means that you have to know the term before it. So like, let's say I gave you like a of 0, right? And then you wanted to solve for like a of 5 using these formulas. That means you'd have to do it like 4 times beforehand. That makes sense? Yeah, cool. Let's see. How would we make a general formula for this sequence right here? This geometric sequence. An is equal to, so let's say, once again, we had a of 0 was 1, right? So if we plug in 0, that means that we want to get, so it would basically be an equals probably 2n, right? That way, if we plug in 2 to the 0, we get 1, or 2 to the 1, we get 2, 2 to the 2, we get 4, right? Okay, so that makes sense. Sometimes, let's say somebody said that this was a of 1, then instead of a of 0, then keep in mind this would be 2n minus 1, but I did not define it that way. Therefore, we'll just keep it as that. Yeah, I defined it as 0, so we'll keep it at that. How about that? How about this one? This one's a little bit more complicated. This one might actually force me to think through it. However, how do we do this arithmetic sequence of 1, 2, 3, 4? So we have at the beginning, we have a 1, right? And then at the end, we have, well, if this is n, right? So this is n is 0, this is n is 1, this is n is 2, this is n is 3, right? So notice that this value right here is n plus 1, right? So we're going to have 1 plus the last value here, because it's n1 plus 1. Doesn't that mean that the average of these values in a sequence like this, the average would be multiplying basically the first, or be adding the first value and adding the last value and then dividing by 2. Doesn't that get you the average value? Do you guys see how that's working? It's going to get you the average value. So we're going to do 1 plus, once again, that would be n plus 1 in this case, and then divided by 2 would get us the average. And then how many values do we have? So in this case, we have 4 values, even though we're on n equals 3, right? So what that would mean is that we have a total of n plus 1 values. So we would have to multiply the average by the total number of values that we have. So we get n plus 1. And once again, keep in mind that this formula is never going to be exact. This, like they might give you another question where it's like, instead of having n plus 2, you have n plus 1 over 2 times n here. Know that the reason here that it's n times plus 2 times n plus 1 over 2 is because I started with basically saying that this indices is 0. But notice that if we were to make this not 0, if we were to start at 1, this would become n plus 1 times n over 2, which is the actual formula for a arithmetic sequence. So hopefully that makes sense to you guys. Chat, let's see. Can you do a of n equals n plus 1? Let's see. So for this, you're saying for, I just dropped. Oh, this would be actually for the general formula for the sum, by the way. Yeah, I don't know why. Yeah, you're right. This is a sum formula. And let's see, you're saying just to find n at that point? Yes. So if you were to find n at that point, you're saying a of n, like for example, a of 0 is equal to 1. So yes, it would just be a of n equals n plus 1. Yes, you're correct, Nick. This is a sum formula that I was deriving here. I should have said that at the very beginning, but didn't. But we'll get to summations now. No problem. Okay, so now we have some summation rules. Once again, this is really like Calc 2 content. Is anybody here like who here? I don't know, for you guys, I think Calc 2 is a co-rec for this class, right? I have literally no clue. So like, is everyone here like, have they taken Calc 2 already or no? If you're taking Calc 2 right now, have you done summations yet? Okay, cool. I was just wondering because I just wanted to know like the general background knowledge on this to see how far in depth I should go over it. But here's some basic summation rules. If we have a sum, and let's say we have like the sum of like 3n, note that this is going to do the same thing as basically this right here. We can take this constant and we can move it from here to in the front, okay? Now, if we have a sum of 2 functions, we can actually separate the 2 functions and consider them as completely different sums, okay? So if we have the sum, once again, we have 2 functions, we have a function f and a function g. We can then split them apart and basically say we have the sum of the function f and the sum of the function g. Now down here, what these are describing is how do we shift our initial indice? How do we shift, like if we wanted to, like if we had a summation and it starts at n equals 1, and let's say we wanted to change it to start at n equals 0, or vice versa, we had it started at n equals 0 and we wanted to change it to n equals 1. How do we actually do that? Now, this might look a little bit confusing right now, but don't worry, on the next slide, I do have some practice problems to show you like what I mean by this. Also, something I didn't include on the slides, but I do just want to mention real quick. If we get like one of these guys, let's say, it's so bad drawing. What am I doing? Thank you. So if we get one of these guys, right? It's just some function. What is this saying? Yes, but okay. And basically, how we want to do this, what I always say, the way to think about these, you guys, obviously, everyone's taken programming 1, right? And then like most people are probably in programming 2, or they've taken programming 2, right? Now, the easiest way to look at this, let's compare. Let's talk about how would we connect this to programming. This is basically a double for loop. This is how you do these. Evaluate these the exact same way you would evaluate a double for loop. Keep that in mind. So like first, like maybe if I was 1 and m was 2, and then j was 1 and n is 3, we would basically say, we would first go I is 1, while j is 1. So we'd say j is 1, I is 1, and then we would go to, we would say j is still 1, I is equal to 2, and then we would go j equals 2, I equals 1, j equals 2, I equals 2, ... etc. Right? Okay, do you guys understand that logic there for the double? I realize I didn't add that to the slides, but I've seen it in a lot of practice problems and stuff, so I just wanted to real quick touch on that just so that everyone has that in their mind in case that happens to show up. Yeah, it's like Javi just said, it's basically a nested for loop, like a double for loop, whatever you want to call it. Yeah. Oh, Logan said that in chat, nested. Okay, cool. So now we have this formula here, right? And first we want to calculate what this is equal to. And then after that, we're going to adjust the index, the starting index to be one lower and then one upper. Okay, so we can kind of get practice with this concept. And once again, if it shows up on the exam, hopefully we'll be able to do it. So we're going to start off. How are we going to sum this up? So we're going from 1 to 4. So what I'm going to do is I'm going to start off by saying basically n squared plus 1. We're going to say 1 squared plus 1 plus 2 squared plus 1 plus 3 squared plus 1 plus 4 squared plus 1. And that would be it, right? Because we're just going from 1 to 4. So this is going to be 2 plus 5 plus 10 plus 17. 2 plus 5 is 7 plus 10 is 17 plus 17 is 34. Okay, so that's our final answer, right? But now we're going to split this into two different problems. The first of which we're going to have a starting index n equals 0, and the second of which we're going to have starting index n equals 2. Now, so first what we're going to do is we're going to write this up. And we know that n is going to be 0. So if I go back a slide, right? When we're going, notice that we're going from n equals 1 to n equals 0. So that means we're going to go down, right? We're going down 1. So if I go back this slide, let's see. So here's our n equals 1, n equals 0. We're going down 1. Notice that our k becomes k minus 1, and our a becomes a n plus 1. Ooh, there we go, n plus 1, right? So I'm going to erase this for now just so it's not messing up the slide, but you guys can see. So there we go, good enough. You can see how basically what's going to happen is we're going to subtract 1 up here. We're going to say 3 now because it's 4 minus 1, right? Now notice that when we do 0 to 3, how many total values do we have? 0, 1, 2, 3, 4, right? And when we do 1 to 4, how many total values do we have? 1, 2, 3, 4. Notice your total number of values is staying the same no matter what. You're just basically shifting them. And then after that, we're going to have to go to our original function. And instead of plugging in n, we're going to plug in n plus 1. Because, for example, when we plug in 0, we need to get the same result as if in the previous summation we plugged in 1. So we're going to go to n squared plus 1. And we're basically going to say this is now going to be, instead of n squared plus 1, we're going to say n plus 1 squared plus 1. Okay, so now, no, I went to the next slide and I showed the answers. What have I done? Okay. So we're going to go to this, we're going to simplify this. Let's see. I think somebody, someone in the audience just said it. I'm just going to work it out just so everyone sees it. So we got n squared plus 2n plus 1, right? Plus 1, which is equal to n equals 0, 3, 2, n squared plus 2n plus 2. Hold up, my phone just buzzed. I'm going to silence this thing real quick just in case.
And let's say for 2 minus, you do n equals 2 and then n minus 2.
Let's see. Are you saying for, to put it to 2? So yeah, basically our n would become, like you said, n equals 2. And then remember that we have to have the same total number. So this is now going to go to 5 because we're adding 1 right there.
Wait, you're adding 1. Okay.
Yeah, so we add 1. And then after that, we're going to plug in n minus, well, let me make sure, let me add another parentheses real quick. We're going to say n minus 1 squared plus 1, which is going to get us, let's see, n squared minus 2n plus 1, which is equal to n equals 2 to 5. And this is going to get us n squared minus 2n plus 2. Now, once again, notice I say right here, prove equivalence, prove that they're the same thing. So what I'm going to do real quick is I'm just going to plug in all the values and show that we still get this same 34. So I'll move this up here real quick. Say again?
The way you prove quotes getting the same sum, yes?
Yeah, we're just proving that they get the same number. So we're going to get n squared plus 2n plus 2. And also, you're not only going to notice the same number, you're about to notice something else. It's pretty interesting. N squared plus 2n plus 2. So we're going to get, we're going to start with 0, right? So 0 squared plus 2 times 0 plus 2 plus 1 squared plus 2 times 1 plus 2 plus 2 squared plus 2 times 2 plus 2 plus, let's see if I can fit it, 3 squared plus 2 times 3 plus 2, which is equal to, we're going to get, let me actually erase that parentheses. We're going to get 2 plus 1 plus 2 plus 2 really is 5 plus 2 times 2 is 4 plus 2 is 6 plus 2 to the power of 2 is 4. So 6 plus 4 is 10. And finally, we get 3 squared, which is 9 plus 2 times 3, which is 6. So 9 plus 6 is 15 plus 2 is 17. So do you guys notice something here? Yeah, these are literally the same values. They're the same exact order, which obviously is going to give us still 34, right? And then if we were to do the same thing down here, I will write it real quick. Right here, we're going to get, we're starting with 2 this time, right? So 2 squared plus, or actually now minus, right? Then I go 2 squared minus 2 times 2 plus 2 plus, now we're going to go 3 squared minus 2 times 3 plus 2 plus 4 squared minus 2 times 4 plus 2 plus 5 squared minus 2 times 5 plus 2. And now what we're going to get is we're going to get 2 squared minus 2 times 2 is 0 plus 2 is 2 plus 9 minus 6 is 3 plus 2 is 5 plus 16 minus 8 is 8 plus 2 is 10 plus 25 minus 10 is 15 plus 2 is 17. Once again, notice it's the same order and we get 34. So does this hopefully make sense to you guys how to prove, or not prove, but like how to switch up the indices when you're doing these summations? Okay, cool. All right, so now we got some properties. Let's see. I do have all of the, I mean, as you guys saw, I got the answer key slide in case some of these are hard, but let's see, what is an input? Yep. What we put in? Yeah, works.
Algorithm with black box.
And what's the output? So what we get out? Now, what does the output have to do with? Has to do with 2 things. Codomain and range, yep. And what's the difference between the codomain and the range?
Also codomain will fall here in what you're actually there.
Right, so what we had someone in the audience say is basically the codomain is what is possible, the range is what you actually can get. What that means is basically when we look at the codomain, you know, your codomain could be all real numbers or something, but maybe your range, you can really only get integers or something based on the function. So that would be our codomain versus our range. Definiteness, however you pronounce it. But basically, what does this mean? Any guesses? Yeah, so what this really means is that the algorithm is defined properly, which means that basically you have the same steps each time in the algorithm. So you always have a specific order of steps in an algorithm. So I'm going to write specific order of steps. Then we have correctness. This one's kind of obvious, but it's basically the stuff that you get out of the algorithm is actually what you expect. So I will say the output matches expected values. You know, if I made let's say I made an algorithm to calculate factorials using like a recursive function or something, and I put in, you know, 2 as my input, I would want to get 2 as my output. If I put in 2 as my input and I got like 4 as my output or 6 or something, clearly we have some form of error there. Finiteness means that it's eventually going to end. Finite, opposite of infinite, so that makes sense, hopefully. And then we have this effectiveness, which is actually very similar to finiteness, but it's basically saying each individual step is finite. If we look at the algorithm, we could split this up into the steps and see that they are all individually possible to run. So I'm just going to write this as, let me think, individual steps can be finitely executed. Yeah. There you go. And then generality, any guesses? This kind of sounds like general. What do you guys think? It works for a lot of things. Specifically, it works for everything that's in the domain. So if we made a function that's meant to take in an int in a program, you know, it should work for every single int. There should not be integers that it doesn't work for. That means that we have to do stuff like edge cases, base cases. You know, when you're working on projects, if you ask for an input that's an integer and somebody puts in a 0, and then in your code somewhere you're dividing by that number, you need to create a case where if somebody puts in a 0, you know, it gives them a proper error message or something, you know, spits out you cannot divide by 0 or something along those lines. You need to be able to have a solution for every case. So works for all members in domain. And then finally, efficiency. There are two important things when it comes to efficiency. Any guesses? That is one of them. That is for the, what does that have to do with them? Yeah, so I heard someone say it, time complexity. So that's one of them, time, right? So we have to look at a fast / good time. And then there's actually one other factor. Are there any guesses? Memory, yeah, storage. Low storage. We don't want to use any solutions that are going to take a lot longer, which goes into the time complexity, which is something we will obviously be getting into very soon. We also do not want any algorithms that they store a lot of excess data. We do not want algorithms that take up a lot of extra memory that we don't really need. There are the answers, like professionally written, whatever you want to call them, fancy definitions. Most of these I write on myself with help from like the textbook and stuff. So yeah. So now we have function growth, and in order to teach function growth, I just thought might as well just jump straight into a problem. Once again, this is a calculus concept. I feel like you do this stuff in all three calculuses, basically. We're going to be putting these in order of which goes to infinity the fastest. Yeah, so when you think about what is this, once again, for everyone who's taking calculus, basically we're looking as the limit goes to infinity, which one of those is going to be the greatest and go to it faster. So we really, do we care about the short term? Do we care about like, what is at 1? No, we don't. We're really looking at the long term, what's going to end up happening. So if I look at these, let's see, you guys want to help me? Let's put these in. What's the first? Any guesses on what the first one is looking at this list? Oh yeah, I was going to do ascending order. Ascending order. So the slowest one first. Yeah. Log n. You were right, going like descending order, but I didn't specify that, so that's my bad. So log n. Yep. And then what's the next one? There's actually one that's before. Yeah, it's log n squared, because remember, if we go back to our basic log like rules, right? This thing is equal to, we can take this 2 and we can put it to the front. So we actually get 2 log n, which is going to be before n log n. But then that is our third one, I believe. N log n. How many numbers did I add? So I added a total of 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there are 10 total. Say again? Yeah, I have an n. We do have an n. How about this? I will start crossing them out as we add them. So we were done with this one. We are done with this one. We're done with this one. And we're done with n. And then let's see, what is next? Now we have, I believe, probably n squared. N squared, n cubed. Yeah, 2 to the n. And then n factorial, I believe. Yeah. Yeah. N factorial is slower than n to the n. Yeah. And then in the short run, yeah. In the long run, obviously everything kind of gets far. But then n to the n.
And to the power of n factorial.
And then, yes, this is the final one. If you make an algorithm with n to the n factorial time complexity, guys, I'm sorry, but please, like, get out of CS, okay? Proper leak code answer? Yeah, leak code, guys, grind the leak code.
Yeah, this one no.
I don't know, man. If you're doing the leak code interview and you code your algorithm and they're like, all right, so we got 2 pieces of data here. And this is gonna take us so
Hold on.
I miss
Oh yeah.
what did I do? Are these swapped? I don't know.
Yeah, when you're
Let's see. So you guys are saying n to the power of n is slower than n factorial? What's up? Log n squared. Oh, I have to switch these on the answer key. I see. Oh yeah. No, I see what you're saying. I don't know why I put this one first. Yeah. It's this and then this. Is that what you guys are saying?
Yeah.
Yeah, that makes sense.
If you did like 3,
Yeah.
3 will be faster, it'll be slower than 3.
Yeah. So keep in mind once again, that was just a mistake on my part. But keep in mind, assuming that n is a big number, that means log of n. Now in our case, log of n is usually log 2n. So assuming n is a number that is larger than 2, this means that this is going to be greater than or equal to 1, which means that yes, this goes faster than n. Yeah, that was my. We're good.
Good job.
Facts. All right, so now we have big O notation, and we also have, along with big O, we have big omega, and we have some really, really fancy definitions there. However, I'm going to break down these definitions so that hopefully we can begin to understand them. I also have some pretty extensive notes on this stuff to make sure I don't explain this wrong, because this stuff gets a little bit complicated, to say the least. But basically what this is saying is, for big O, we can find a function that if we put a constant in front of it, any constant, it doesn't matter which one, a constant c, it's going to go to infinity faster. Now, for the one below it, it's saying for omega, and so O gives us our worst case, because it means that we are having more iterations than the original function. For omega, we're doing the opposite. We're having a function where if we put a constant in front of it, it's going to be going to infinity slower, which means that it is a best case scenario. And then you have theta, which theta is basically when you have both O and omega, both omega and O, I guess I have written up there, but you have both of them, right? And during that, we call that average case. When you have a function that maybe you put one constant and it's going faster, you put another constant and it's going slower. So yeah. All right, so let's find the theta time complexity of 2n squared plus 2n plus 1. So once again, what did I mention that we're doing when we're finding theta? We're finding the big O, we're finding the omega, right? And so I'm going to split this up into 2, right? We basically need to say, we need to find a function that is both big O and omega. So we'll start with the big O, right? We're going to start by writing the original equation down. Plus 2n. Now remember, we need to find a function that we can just have a constant in front of, that this is always going to be less than. So, and on top of that, we need to find basically as this goes to infinity. Now, if you're finding something as it goes to infinity, what that means is, once again, we're not really interested in the short term. We're interested in the long term, which means what we can do is we can find a function that as long as it's above a certain number, it makes sense. And that goes into what we call witnesses, right? So this thing's called witnesses. We have a k. What k is saying, if we go back to our definition right here, also, it seemingly is going to be pouring rain outside. That's crazy.
Fitting for a street example.
Very, very fitting. It's like the tears shedding down. Okay, but so notice, like I said, we're going to infinity, so we're going to have some k value, where basically what that means is n is going to have to be greater than or equal to k. You can set it to 1. Let me check. Yes, you should be able to set it to 1. You're correct. So we're going to have. See, I would have to check. You probably could set it to 0, and then you'd have to change up the constant. Like whatever k you have and whatever constant you have, there's really an unlimited supply, oftentimes, of possible combinations. You just kind of do whichever one you see easiest. And also, I was explaining this earlier to some people. Like, keep in mind when you have a k and a c for these witnesses, you just need to prove that one of them exists. You don't have to like prove all of them exist. You don't have to like get a specific one. You just have to find a pair that exists that makes sense.
How does the k, how does change the k change out here?
We will see that in just a second. Yeah, we'll see that in just a second. So k has to be above a certain value. And your other witness is c, constant before g of n, where g of n is the function that is representing the big O or big omega or whatever, right? So we have 2n squared, 2n plus 1. And we need to find something that this is less than, right? Now, here's the thing, right? We have a plus 1 there. So whatever we make this less than, well, theoretically, right? Let's say we said that k was equal to 1, right? What this means is that, k is positive. We can say that if k is at least 1, wouldn't this be less than or equal to, as long as it's a positive number, 2n squared plus 2n squared plus n squared, right? Because think about it for a second. If n is 1, then n squared is also, or if n is 1, then n squared will be 1. So that means we have this plus 1 here. If and then n squared can only, changing it from n to n squared, if it's greater than 1, squaring something can only make it go up. So no matter what, we have that this function right here, assuming our k is 1, which means assuming that n is greater than or equal to 1, we have this must be less than the function on the right. Do you guys see that? Okay, cool. So now we're going to simplify that. We have this is going to be 2n squared plus 2n plus 1 still on this side. If we simplify this, what do we get? We get 5n squared. Yeah, so then we can see right here, we prove that a k is 1 and a c is equal to 5, because that's our constant right there.
Big O is n squared.
Big O of n squared. And once again, you could prove this with whatever you really want. You could say, screw it, guys, let's make it is less than 7n squared. And we could say our c is now 7. That would still work, technically. You could still do that. Or you could say, also, what if we made our k 2? Okay, like you could do that too, technically. And once again, that would work. It doesn't really matter. Let's say the way you might need to change your k value is sometimes if you're doing big O and you have like subtraction and you need something to like cancel out. So if you have like an n squared minus 4.
What I'm saying is like if you plug in k is equal to 2, then how would that change the function?
This function right here,
Yeah.
in the long run, it wouldn't change anything. So
Would it just remain 2n squared plus 2n squared plus n squared? If k is equal to 2?
yeah, This, because think about it, like if k was equal to 2, you would still have this function being less than or equal to this function.
And then you would just have k equal to 2, which is equal to 5.
Yeah.
Yeah.
Yeah, so like no matter what you plug in, as long as it's greater than 1, you're gonna get this. And sometimes it could be 0. It really doesn't matter. Just find something that works and prove it and write down this is the witnesses. The witnesses are k equals 1 and c equals 5 in this case. But I said k equals 1 because I wanted to change this to n squared. And in order to make an n to an n squared get greater, like if it was less than 1, like if we did like 0.5 times 0.5, that would become 0.25, which would actually make it go down. So that's why I decided we want to make it at least 1. So that way when I square something, it's going to go up no matter what. So now we have to find the omega time complexity of this, which we're basically doing the same thing, but this sign that's a less than or equal to, we need to find something that is greater than or equal to. So 2n squared plus 2n plus 1. So yeah. So once again, we could say, let's say our k is 1. Again, we're going to say it's positive, okay, because we're going to infinity. Notice this is always going to be greater than or equal to. If we take away this 1, right? If we add 1 to something, it's always going to be bigger than whatever it previously was, right? There's no possible way to add 1 to something and for you to get a smaller value than what it previously was. So we can say that this is greater than or equal to 2n squared plus 2n, right? And then once again, we know that n is a positive number. So because we know n is a positive number, we can say this is greater than or equal to 2n squared. Now, the fact that we know that this is 2n squared, greater than or equal to 2n squared, we can rewrite this 2n squared plus 2n plus 1 is always greater than or equal to 2n squared when n is greater than or equal to 1, aka our k equals 1, right? Which, what that means is that we can say, here's our constant, it's our c value, c equals 2. So our witnesses are c equals 2, k equals 1, and we can say that this is big omega n squared, right? And then finally, notice, what do we have? Yep, both of them. So now we can say big, I don't even know if you're supposed to write this as big theta, but I'm writing it anyways. Theta of n squared, right? Yeah. I don't know, I just like writing big, why not? But anyways, what's up? Right here. So basically I was saying like, so for this one, I was comparing with this. Remember that 2n squared, if our value is more than 1, is always going to be greater than 2n. And then for this last n squared, I was comparing with this plus 1. Once again, remember that if our n is greater than or equal to 1, then n squared is going to always be greater than or equal to 1. So basically, this is a comparison with this number, and this is a comparison with this number. No matter what, the one in the middle on the right will always be greater than the one on the middle on the left. And no matter what, the one in the middle on the, or the one on the right will always be greater than the one on the right on the left. There you go. That was a little confusing, but those are just direct comparisons. So hopefully that kind of makes sense. These concepts here are like super duper complicated to explain. So it just kind of is what it is. But yeah. So we're going to find, we're going to move to the second. I'm going to erase that circle, make it a little smaller so we can still see the question. We're going to go to the second question, and it's just, this time it's just big O time complexity of 3n log n squared. So keep in mind, for these problems, sometimes you might have to bust out some of those old algebraic rules. So what is 3n log n squared equal to? We went over this like a little earlier. So yeah, we're going to take this, we're going to move it out. We're going to say it's 2, 3n. I know that these steps are a little redundant. I'm just writing it out so everyone can see. 6n log n. Okay, so we can get 6n log n. Now, what can we do? Once again, we can say k, let's say, so in this case, right? Remember in this class, in a math class, when you have log something, this would mean log 10, right? However, we don't do that in this class. When we have a log, we're assuming log base 2. Now, what is the smallest number that we can use in log base 2 to something? that is at least 1. 2, right? So we're going to say 2 to the power of x is equal to what? And we can know that 2 to the power of 1, or actually, I guess it would be rather saying, yeah. So in order to get log base 2 equal to 1, we need something to be at least 2, right?
Okay.
2 to the power of x is equal to 2, and we need x equal to 1, which means that, yeah, we got 2 right here. Okay. So basically what we're going to say is, in order to make this log of n at least 1, so that we're not decreasing in any possible way, shape, or form, I'm going to say that our k value is 2. That way, if I said it was 1, right, then if we plug a 1 in right here, we're actually going to get like some fraction, because in order to make 2 to the power of something equal to 1, you have to have a fraction there. So that's why for this problem, I'm going to say k equals 2. And notice that when k is 2 or greater, we can say that, well, really what we have is 6n log of n, right? We can say it's always going to be less than or equal to any function. What do we want to say?
Log n.
Well, really what we have here, when I look at this problem, actually, I mean, this is basically already a base case. So we could just say that 6 is a constant. We could say this is 6n log n, which is going to be less than or equal to 6, or rather, I guess you could say here, right? We could just say this: 6 log of n is less than or equal to 6n log of n. So we could just say our witness, really, we could just say our witness is k equals 2, c equals 6. I think you actually technically could, because either way, if this was 1, it would still be greater than, say, if we added like a 7 here or something. But we could say that those are our witnesses, and thus this is big O of n log n.
Okay, so that's.
Yeah. So hopefully that also makes sense to you guys. Everything kind of clicking? Yes. Okay, so for the second one, let's take a look. So I said k was 1, and I was looking for, let's see. So really, k for this one could like, I could be like basically anything that's greater than 0 or 0 or greater, because if you think about it, right? We know that if this was a negative number, for example, right? Then we wouldn't always have this this value right here being greater than this value right here. Like if this was like a -1, then 2n squared plus 2 times -1 would actually be less than 2n squared, right? So that wouldn't work. But I'm pretty sure if we were to use 0 or 1 or like just basically any positive value, like it works. So I just chose 1 just because like, okay, it's like just the easiest off the top of my head, you know. You just have to make sure for this example that it's positive.
And I see what you want to find, what's called the big omega, you would just do, I don't know.
Let's see, for big omega, this one, yeah, you're basically like,
Would you do big, would you do 6n log n, you do 6n?
yeah, you could just like, for big omega, you can always just do the same thing. You could say it's going to be greater than or equal to. And thus, once again, it would also be big omega, and this one would be theta of n log n, right? N log, yep.
Theta, you have to find the bigger and the omega.
Yes, you have to find one that matches. Note that means that not all functions will have a theta. If you have a function and it's called optimal, right? The optimal big O is the smallest big O, and if a test question asks you for optimal big O, that means find the smallest one. The optimal omega is the greatest omega. So once again, if something asks for optimal, it's saying to find the greatest omega. Because think about it, right? If you say omega for best case scenario and you have like n squared as a function, okay, technically that is omega of n, right? And that's also omega of constant, but that's not really useful information. But to know that it's omega of n squared is actually kind of useful. It's the optimal. And now we just have searching and sorting to do after this stuff. So, and then we'll be done. What time is it right now? Anybody know?
8:24.
All right, we'll try to,
You're almost at the 8:30. Come on, you can do it.
I think we have a total of 3 more slides.
Bro, come on, look up.
We have a total of 3 more slides, I think.
Bro, come on, finish showered on the way home. Let's go.
It's surprising considering I'm in a room with CS majors, but you know.
Bro, I went out today, God said, no.
All right, so for this linear search stuff, it's just something I want to mention. I don't know if I have it on here. Yeah, I forgot to write it for this one, but this is going to be big O of n squared. Keep that in mind. But for linear search, basically what you're doing. Oh wait, no, big O of n squared. I take that back. This has nothing to do with that. I read the wrong thing. Hold up. But anyways, for this linear search thing, basically what we're doing is we're going to be going. Let's say we're searching for 6, right? We're literally going through this list until we find 6. So like first we check the first one, it's not 6. We check this one, it's not 6. Check this one, ... Until we get to 6. And then we find 6 and we see, oh, 6 right there. Now what index would this be at? Remember for this exam, we're using Java syntax. So yeah. So it'd be 0, 1, 2, 3, 4. Yeah. So this took 5 checks. Now let's say we took the same thing. And let's say we do binary search. Binary search is where you're basically splitting the list up into halves every single time, and you're checking, okay, did we get to the value? Is the value greater than? Is the value less than? So because of that, because we're splitting it up into halves, it actually means that the time complexity of this, since we're dividing by 2 each time, actually comes out to log n, which is very, 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 very good. Okay. Now, so basically what we're going to do, we're going to say the starting index is space complexity. Space complexity would be for like how much like memory we have. I don't think we have to know it. No. Yeah, I don't think we have to know space complexity. So let's say we have a 0 starting index, and we have this is 0, 1, 2, 3, 4, 5. 0 plus 5. What's 0 plus 5, guys? 5. Okay, what's 5 divided by 2? But we're using Java, and when we just divide something by 2 in Java, what happens? So yeah, we get 2. We chop off the 5 because we're just assuming this is an integer value, right? So basically, we get the index of 2. And if we go to 0, 1, 2, we can see this is our middle, right? Now we're looking for 6. So what do we see? We see 6 is greater than 2. So now we know that we need to check the right half, okay? So we split this up into the right half, and now we have 3, 4, 5, right? Once again, 3 plus 5 is 8 divided by 2. That's 4. So we know this is our new mid value. We see that as 6. It only took 2 times to find the 6. And a lot of times algorithms will stop here. And I believe for this exam, we need to know that it stops here. Now, I've seen a few algorithms coded where they decide, all right, guys, we're not going to stop here for binary search. So sometimes they force you to basically get to where you only have one value in the list. And that's that orange that I have kind of highlighted there, where it basically forces the list to keep going until there's only one. The way that works is if you don't have a condition checking for if it's equal, you only have one that checks for like if it's less than or equal to or greater than. But that's just so inefficient. So I don't see why you'd actually do that. I just wanted to add that because some people might have seen it that way before, and I didn't want people getting confused. Yes. Yes, and that was definitely, you can see this note right here. Oh, wait, no, that's not I did not add the note, but yes. And that was actually something I was about to mention. Keep in mind, notice when I did this example, this was not a sorted list. When I did this example, this list is already sorted. And that's why we go from searching. Now, all of a sudden, we see why is sorting important, okay? Sorting is important so that when we search for data, it's much easier. You know, if I have a list of names, right, of everyone in the class, and I need to find, let's say, a student ID of a certain person, and I have basically the list of names, and then I have their student IDs on one column. So what I'm going to have to do is I'm going to have to look for their name in the left column and match it with their ID, right? But if their names are sorted in alphabetical order, it's going to be a lot quicker for me to find their name than it's going to be for me if they weren't in alphabetical order, and I literally just have to check every individual one, right? Makes sense. Yeah. So we have insertion sort, right? Insertion sort, what it's doing is you're going to check, you're going to go through the array. You're going to check each individual like pair of numbers, basically. And then if by the chance that you have the number on the right is less than the number on the left, you're basically going to take that number out and put it to its correct place. And by put it to its correct place, I don't mean you just switch it with the number in front of it. I mean, you're going to check it, switch it, and then you're going to check with the next one in front of it and switch it again, and you're going to go until you have it in its right place. So for this example, we have 4, 5, 2, 1, 6, 8. You can see I compare 4 and 5. That's already correct because 5 is greater than 4. Compare 5 and 2. That is not correct because 2 is less than 5, right? So basically what I'm going to do is I'm going to compare 2 to 5. I'm going to say 2 is less than 5, so we put it there, and now 5 is here, right? And then after that, I'm going to say now we're going to have 2 here, and now after that we're also going to compare 2 to 4, and we're going to say 2 is also less than 4. So now we got to X this out, make this 4, and make this 2, and that's how we get to this pass right here. Merge sort, I do have a picture of merge sort in this presentation. We can go over it. I don't think we're going to need to know merge sort like extensively. I think the biggest thing with merge sort is know that its time complexity is n log of n. That's like the only thing I think we'll need to know. Yeah, I have that actually there. Yeah, sneak peek. I posted a picture of that because I do not feel like fully explaining that. Yeah. So anyways, then we have the next one. So let's see, we compared 4 to 5, we compared 5 to 2, and then we're going to compare 1 to 5 here. And notice that we're going to bring 1 all the way to the front because it's the lowest one. And then after that, we're going to compare 5 to 6. And we're going to see that that's the correct. And then we're going to compare 6 to 8. And then we'll be done. You guys see that? So then we have bubble sort over here. First, basically what we're doing in bubble sort, I put all the passes down, but basically the passes, it's like you're stopping individually for every pass. So that's why I put some space in between them so I could write down what's actually going on. So we start with 4, 5, 2, 1, 6, 8. So basically what this is going to do is first we're going to start with this, right? 5, 2, 1, 6, 8. So we're first going to compare 4 to 5. We see that's in the right spot. So we're going to have 4, 5, 2, 1, 6, 8, right? Now we're going to compare 5 to 2. Notice that 2, we're comparing this, 2 is not in the right spot. But basically, instead of like insertion sort, where you put it all the way to its right place, we're not going to put it to its correct place. We're just going to switch it that one time. Then we're going to compare 5 to 1. We're going to compare 5 to 6, and that's in the correct spot. And then finally, we're going to compare 6 to 8. And that's kind of in the correct spot anyways. So then notice that this is how we match 4, 2, 1, 5, 6, 8 is how we match our first pass. And that is one pass right there. That is like all of those operations. Notice we did that like n times or something, right? But it's all still, this was our original starting. So this does not really count as one. Notice we did that n times. And that was for one pass, okay? So now we're going to go through, we're going to do our second pass. We're going to go from here. So we're going to compare them again. We notice that 2 is less than 4. And then we're going to compare 4 and 1. We're going to go 2, 1, 4, 5, 6, 8. We're going to see that 4 and 5 are in the right spot. And then we're going to go 1. We're going to see 5 and 6 are in this correct spot. And we're going to see that 6 and 8 are in the correct spot. 2, 1, 4, 5, 6, 8. Yeah.
Basically, it looks at one, looks for like one of the like place.
Yeah.
It tries finding whatever it's one and not have more not more.
Yeah, what you just described is actually very similar to selection sort. Yeah. So then after that, we can do this again. This process, we can go through it again. We see that 1 and 2 are not in the right spot. So we're going to switch that. So now we have 1, 2, 2 and 4 are in the correct spot. 4 and 5 are in the correct spot. 6 and 8 are in the correct spot. Why do I have a pass 4 right here? I think this might have been a typo. Don't pay attention to this. Pass 3, we have, let's see, what am I doing? 2, let's see, we have 2, 1, 4. 5, 6, 8. And we have 1, 2, 4, 5, 6, 8. So that's correct, right? Yeah, so this is correct right here. I'm not sure what this past 4 thing is. I must have like accidentally copy and pasted something a second time, but don't pay attention to that. I will update this for the actual slide deck. And this is basically where we would stop. We would do one more pass after this pass 3 to make sure basically when we see that there are no longer any swaps, when we go through the entire array and we see there are no swaps in the array, that would be the last pass. And that would basically say that we're done. So actually this pass 4 would happen, but I don't know why it was in the wrong order. There we go. So those two just had to be switched. So yeah, we had 4 total passes. That last pass was checking to make sure we were done. Yes, it's actually on the next slide. What do you know? Crazy. So notice also the big O of these is all n squared so far. So we have a selection sort, right? Basically what we're doing with selection sort is we're finding the smallest, well, it depends if you're sorting in ascending or descending order. If you're sorting in ascending order, you're going to find the smallest value and bring it to the front. If you're sorting in descending order, you're finding the greatest value and bringing it to the front, etc. So in this case, I was sorting in ascending, just so you know. So anyways, basically we look at this array, we see that the smallest is 1, we bring 1 to the front. Then the next smallest we see in this, we see is going to be this 2. We bring 2 right here. Right. Yeah, and also it's going to basically always going to be going to the front, but then each time it's going to go to the front plus 1 for each pass, like the front changes. So once we have something go to the front, the thing is locked in place because we know it is like the least. So our next smallest that we see in this list is 4. So we're going to bring this to the third. And then the next is 5. 5 is already in the correct spot. 6 is already in the correct spot. 8 is already in the correct spot. And then we are finally done. So that was a really, really quick explanation. Do you guys understand what was going on there? Okay, cool. So yeah, then we got big O of n squared. And then finally we have merge sort. This is like merge sort's so complicated. So like to explain at least. So that's why I decided, okay, I'm just going to take a picture from the internet and post it on here. Basically what you're doing with merge sort, you are splitting it up. Splitting it right here. Splitting it up. Splitting it up. Splitting it up. Splitting it up. Sorting. And then basically combining it back together. So now what's the splitting going to be for the time complexity? If you're splitting something up, what's the time complexity of just splitting something into halves going to be? Log n, right? So think about it, like if you have like a total number and you're splitting it by 2, it's gonna be log n. But then what's that combination factor gonna be for placing each thing in the right spot? N. So that's how they get this time complexity of n log n, which I think if this appears on the exam, I really think that that's basically all we're gonna need to know is just know that it's n log n. And know that it's quicker than other sorts, quicker than those quadratic sorts.
Wait, hold on.
You sort what are these? You take what are you sort them into? You split them into equal arrays. When you sort those arrays, you don't do that entire split.
This is just a straight up a picture of merge sort. So yeah, this is exactly what it is. I don't know what to tell you. Like this is from like yeah, this is an exact picture. So yeah, what's up? Linear search is n squared. No, linear search. Actually, I take it back. Linear search is okay. Hold up. So that's basically what we're gonna do here. The maximum times that we could search for something is just n, right? Because we could go like we could check here 1, 2, 3, 4, 5, 6. Yeah. So the maximum times we can have is n. So it's just gonna be big O then. But keep in mind that log of n, which is what binary search is much quicker than n. We're done. Cool. All right, sweet. All right, thanks for coming, everyone. I hope. Wait, there's people with questions in the Zoom. I'll answer those. Thanks for coming, everyone. If you want to leave, peace out. It's kind of pouring out rain, though, so have fun getting home. Yeah. I enjoyed it and good luck on the exam. I'm expecting to see straight 105s tomorrow. I'm gonna stop the recording. See you guys. All right, let's take a look at questions in the chat.
You're not getting into the exam.
You guys are welcome. It's raining. We're talking about thunder and lightning. Are there any extra questions in the chat or no? No problem, Landon, in peace. Yo, what's up, Darren? Doing good.
Thank you for that.
All right, you're welcome.
Good stuff.
Thanks.
Also, the explanation,
What is?
it made more sense.
All right, cool. That's good. Yeah.
For example, let's say if on like on the exam they ask you like prove like whatever is like 1 to 1 and then prove that this not prove but like show that this is like constant, right?
Yeah.
So let's say they ask you show the 1 over x or something. Like how will you do that? Like I don't like show that it's 1 to 1 is if a equals FB. So just like F,
So the thing is, for like somewhere like 1 over x, right? It would depend on the domain. But like if the domain was like all integers or something for 1 over x, that'd actually be false because there's no way you can get 1 over something to be 0.
so you can't
So you would actually, you could prove that it's not by showing a proof by not contradiction. There's a word for it. It's like showing like one case that's trying to think of what it's called.
so you sure like
Basically, you're showing a counterexample. That's what it is.
all right so
Yeah. Well, in that case, like contradiction is showing that two things can't happen at once. But then if you show like one example where it's like that one example is basically showing that it's not for all cases, that's just called just a counterexample. That's it.
so
Yeah.
you sure like f a equals b, you sure that way? Like 1 over x, you do like f a equals b.
You could say once again, you could like say like what if it was all integers, you could literally say, look at the 0. We cannot make this equal to 0. Therefore, this is a counterexample that makes this false.
All right.
Yeah. Yeah. What's up?
Wait, so for this bit, and like you could go like with a worse buffer and just
What do you mean? Like you could make this like 7n squared, right? And it would still work. But like because you still have a constant there. But then you couldn't make this less than 5n.
no, I'm just saying why change all these things squared?
Because we know for 100% fact that this is going to be less than this. And also this changes it into one function that we can put in.
Change this last thing into n.
What do you mean?
Like just the same thing except plus 3n.
Plus n, like, oh, like we add like n like on the end.
Yeah.
Because that would not be one function that we can put into big O. Big O's got to be like one polynomial basically.
With like the same.
Yeah. That you can just put a constant in front of it and it works.
There's also a quiz.
Was quiz tonight?
There is a
Count
quiz.
two?
No, count 2.
No, not for us, not for me.
Okay, we go back to the selection slide. Hey, I'm not sure if you're still here, but
No,
let me, is my screen still sharing?
I'm in person. I just want to say, thanks for putting this on. It's a pretty good.
Yeah, thank you. What was your name again? Colin?
Yeah.
All
we're
right.
in the same space.
All right, yeah, all right, see you.
The one that calls you the clown, when we're the.
All right, listen, serious in the classroom, an absolute clown outside the classroom. Yeah,
Remember that.
all right, see you. All right, Haley, let me get that slide up for you, sorry. I need to get the PowerPoint back up. You said, which sort was it? Where's the chat at? Selection sort. PowerPoint.
I mean, it was
Here. Okay. Wait, that's insertion and bubble. There we go. Now we have selection sort. There you go.
No, for.
Let's see. Yeah, what's up? All right, see you soon. You too. Okay, so like how you know how the first pass? It's not like 1, 4, 5, 2, 6, 8. It swaps the 1 and 4 placement. So for selection sort, right? Yeah, it swaps the one in. Let me look at it again.
Yeah, I can answer this if you want. I actually.
Yeah. But don't you want to take over? Here, wait, hold up. Here's your turn this. We had somebody who wanted to answer for you.
So the idea of selection sort, basically you have one. You have one integer, or let's say you have, can you go back to the slide real quick?
Or see Logan.
So you see you have one here, right? And that one right here is obviously in the wrong place. And it should be here, right? Shit.
Did you, let's see, I can go back.
Yeah, I can go back. Shit. And sick.
Oh, shoot, let's see. And then we're gonna.
Yeah, we're gonna.
And then we're gonna have to share this again.
Yeah, fair enough. I was clicking and trying to draw on it. Yeah, work well. Is that how TA feels?
I have to also go here and swap. Okay.
Can I draw?
So here. Okay, basically you gotta stay. No.
Okay, so you see how one here is in the wrong place and 4 here is in place where 1 should be? What happens here is, let me just right here. It's gonna look a little bad, but I'm sorry. So what happens here is you have 1 here and you have 4 here. These take the place of that and which become 1, 5, 2, 4, 6, 8.
Wait, can you guys hear me?
Why does it swap them? It's a sorting algorithm. It's trying to sort everything into the correct places here. It's trying to sort them from descending order here.
Can you guys hear me?
You're here, right?
Okay, so I was just making sure you guys have to swap, like that's what it is. Cause I thought it was just like you put the 1 in the front and you just like move it to the side, everything, but you swap the first one and then you just keep going.
Yeah, selection sort is all about swapping. It's a swapping algorithm.
Okay.
That's what it is.
Okay, that's it.
The other algorithms before aren't swapping algorithms, they just sort of like sort in place.
Wait, so so for this one, we swap every single time, or do you just swap after the first one?
For selection sort, it's a swap every single time.
Okay, sounds good.
So yeah, these ones swap, and then if you look at this one here, look at this one here, 2, 5 and 2, 5 and 2, swap. Which one? 1,
Okay,
2,
cool.
5, 4. And then it just goes down the list. You see?
All right, cool. Thanks. Just wanted to double check.
No problem.
All right, have a good one.
You too.